Okay, this is our last podcast of our gas unit talking about stoichiometry with gases. And I know stoichiometry is probably not most of your favorite things, but it really is just normal stoichiometry with one more kind of option on what we're going to do. So this is going to be filling out pages 13 and 14. I'm going to do most of that with you and for you, but there's going to be one or two problems that I do ask you to do. So let's get started. Page 13. Actually, this isn't exactly where I want to start. Because we're doing stoichiometry, I actually want to start by looking back at this map that we used back when we started stoichiometry. And remember, we could go from grams or moles of one substance, and we always use the mole ratio from the balanced chemical equation in order to convert between substances. This is the key for stoichiometry, is going back and forth between two different substances, and we do that with a mole ratio. If we don't start with moles, if we start with something like grams, our first step is to get moles so that we can do that. If the question doesn't ask for moles, if it asked for grams, I'd still have to do this mole ratio, then I'd have to add one more step after that, using the molar mass to turn those moles into grams. So this was our old mole map. Now, last class, we talked about and we learned about how we can convert from moles to volume. As long as we are at STP, that's standard temperature and pressure, we can use the fact that 1 mole is equal to 22.4 liters. Now, I've added in this A here to remind you that that substance isn't changing. All I'm changing is from moles to liters. So if I take this idea and I add it in to the rest of those conversions, now on each side of my mole map, I could start with grams, mass, moles, or volume, which I'd measure in liters. So now we have just 3 options of where to start and where to end. So in this original mole map, we're basically just adding another place to go. But still, the way we convert between our substances is with that mole ratio. So this is kind of our new map. This is how it's changed. All we've done is add this idea to it. And you've already practiced using it. So now it's just going to be combining that with the fact that we can convert between substances, because we've been doing this the last couple of days. So now we're just going to add in this. So I'm going to keep coming back to this map kind of as we work out problems so that we can kind of figure out where we're at. So I'm actually going to start by working this first problem, and then we'll fill in that blank in just a moment. And what I'm writing down right here, you don't necessarily have to write down, because I'm going to simplify this in just a moment. But using that map as my basis, and of course this is an equation that needs balancing. So there we go, it's balanced. This tells us to calculate how many liters, my volume of ammonia, produced when I have 5.5 liters of hydrogen. So if I was getting started with this, and actually let's look back at that map real quick, just to kind of think about where we're at. I'm starting with liters of hydrogen, and I want to find my volume, or liters, of ammonia. So to get there right now, what I'm going to do is turn those liters into moles, use my mole ratio from that balanced equation, and then turn those moles into liters. So that is my plan here. So if I start with this, of course, balanced equation, and my given was 5.5 liters of hydrogen, I have to change those liters of hydrogen into moles of hydrogen. Then I can change that hydrogen into ammonia using my balanced coefficients. So I'm putting the hydrogen and that 3 on the bottom, NH3 on top. But it didn't ask for moles, it asked for liters. So one last step, I'm going to turn as moles of NH3 into liters. So this is technically what that map is telling me to do, but especially if you're savvy with some math, or if you're just kind of lazy, you might notice that when I'm multiplying across the top, the last thing I'm going to do is multiply by 22.4, and then I'm going to come back to the bottom and start dividing by 22.4. And if I'm multiplying by it only to divide by it, won't those cancel each other out? Wouldn't I be able to just skip this step entirely? And yes, we can. The only issue with skipping those steps entirely and just doing this one middle step here is that these units are moles. And if I have liters here and I want liters out of my problem, then these should be liters. And that's exactly what we're going to end up doing. So I'm actually going to clear this out. And I'm going to jump back and look at this map for a moment, because what we're doing is skipping this entire kind of process here and just going straight across here. So we're going to go ahead and add that kind of bridge in here. Now I've called this the mole ratio because we're getting it from the same place, the coefficients from the balanced equation. But really, that's a liter ratio now because we're using liters. So we're using the same numbers. We're just understanding that now, as long as we are starting with liters and ending with liters on both sides, then we can use those same coefficients to do it in one step. So this is what I want you to write down. We are going to be using this 5.5 liters of hydrogen, rebalancing my equation, of course, because I had cleared that out with everything else. And now I'm just going to use this, what we used to call a mole ratio from the balanced equation, is now going to act as a liter ratio. So I'm going to put 3 liters of hydrogen on the bottom and 2 liters of ammonia on top. And this gets me my same answer, just a whole lot quicker than what we had done that other way. So when I do 5.5 times 2 and divided by 3, that gives me 3.6 repeating. So I am going to want to keep 2 sig figs. So that is going to be 3.7, or you can put that as 3.6 repeating. It's still 2 sig figs, but it shows it's not quite just 0.7. So I'm actually going to leave it like that. And of course, units and substance. So that is our answer to the first question. Now, going back and filling this in, we are going to use the mole ratio from the balanced equation, but the key here is to use as a liter ratio. So I always forget when I do this, and I try and keep writing out moles, but when I check my diagonals, I remember, oh right, that's supposed to be a liter ratio now. Same numbers, just different units. So that's our new thing with stoichiometry with gases, is that if I'm starting at liters and I'm ending at liters, then I can take that shortcut. So let's look at the second problem. This says to calculate the volume of water vapor produced when 10 liters of oxygen react at 1.2 atm and 25 degrees Celsius. And then there's a reaction. I'm going to go ahead and balance that reaction, just, automatically. And then one thing that I notice is that this is not at STP anymore. And so you might think that we've got a problem, because when we were looking at this before, we were counting on the fact that 1 mole is equal to 22.4 liters at STP. Now, if I'm not at STP, I can still convert between my volume and my moles. It's just not going to use this same conversion. So I'm actually going to add something to this map. And it's still technically going from moles to volume, but since I'm not using this conversion, kind of this highway here, I'm going to add another highway over here real quick. And it might start to look a little weird, but here we go. So if I'm not at STP, then I would have to use this equation, the ideal gas law, in order to solve for either my volume or my moles. I just have to plug in that temperature and that pressure and an R. But if you notice, when I added this section over here, I'm still adding that we can do this mole ratio, or really this is where I said that this is going to be our liter ratio in here, just like down here. But there we go. Changed it over. So I can do this even when I'm not at STP, because I'd be multiplying and dividing by the same numbers that I'd be dividing and multiplying by going this way. So it's the same idea, even though it's not exactly 22.4. So even though it's not 22.4, it's still going to be some other number, and it'll be just kind of undoing what we do to go the long way. So we can still take our shortcut. As long as I'm going from liters to liters, we can use that liter ratio from our balanced equation. So back to here, this question says I have 10 liters of oxygen, and I want to figure out the volume of water vapor. So I am looking for liters of water. So this is going to be a 1-to-2 ratio. It's just going to be liters in our ratio to liters H2O. And I can handle this math. That's 20. Making sure to keep 3 sig figs. And that's our answer. I'm going to go ahead and ask you to do this next problem that we got. So, there we go. Number 2, you do this one. Go and remember to balance that equation before you do it. It's all 1s and 2s, so it should be pretty straightforward. I'm pretty sure you can handle the math on this one as well. And let me know if you have questions, but you need to do this problem in order to get your stamp on this page. Then, question number 3 steps it up a bit because it doesn't start at liters. It starts at grams. But we are at STP, and I have a reaction. So I'm going to jump back to our map real quick just to map out what we're doing here. Here I'm starting with grams. So I have mass, and it wants me to find liters or volume at STP. So this is where I'm starting, and then I'm going to be ending over here. And we actually have 2 different paths that we can take. We can go to moles and then do a mole ratio and then use 22.4 to get to volume. Or I can turn the grams into moles, turn that into volume with 22.4, and then do a volume liter ratio. And both of them are going to end up with the exact same answer, so it doesn't really matter. I'm going to take that second path because I want to practice using this liter ratio. So, going back to our problem, I've got grams, so the first thing I should always do with grams is change that into moles. So, I have the mass, just adding up 1 N and 3 H's, 17.031. And that's equal to 1 mole of ammonia. And then I'm going to go from moles to liters. That was my plan. So I'm going to use that 22.4 number. This is still ammonia. We haven't changed substances with our equation yet, but that's what I'm ready to do now. I'm going to go from ammonia to nitrogen. So that's a 2-to-1 ratio. And this is where I'm using it as a liter ratio, putting that 2 liters of ammonia on the bottom, and then 1 liter of nitrogen on top. So, a little bit weird, not quite as easy as when it's liters to liters, but still, if you got grams, you turn them into moles. We always do this over and over and over again. And then we've practiced doing this a little bit, so this is really the only new step, the only special step that we've got here. So, all of this set up and worked out gives me 16.1 liters of nitrogen as my answer. Now, here's one more for you to work out and do. This is going to be set up and worked out just like that last problem. So we've started with grams, we're going to liters. You technically have 2 paths that you can take, and I already diagrammed those out for you last time. So your setup is going to look a lot like mine with slightly different chemicals. And speaking of chemicals, I'm going to help you with that balanced equation real quick because it doesn't mention the hydrogen part of it. It says figure out how much chlorine is needed to make hydrogen chloride, but remember, you need hydrogen to make hydrogen chloride. Both hydrogen and chlorine are diatomics. Should be pretty easy to balance, but there we go. So, we got that. You worry about setting up and working out that stoichiometry problem. Your answer should be between 20 and 25 if you've done it right. Now, we are going to move on to the next page. And the top of the next page actually makes it seem like we're doing something completely different, but we're not. At the top of the page, it says stoichiometry of gases when not gas to gas, which means we're going to start having to use those grams and moles more. We're not always going to have gases in liters, but that map that I showed you still works. We just have to be really careful about which substance we have and what we're trying to get to. And this mentions to use stoichiometry and the ideal gas law, that PV equals nRT part. That's up on the top up here. We already kind of knew we were going to have to use that. So that's absolutely fine. So there's going to be some times where we have to stop and calculate some moles, solve for N, and then we're going to plug it into that equation to get volume, or vice versa. Solve for volume, plug it in here, and then get our moles. So really, we just have to get started looking at these problems, analyzing what's going on with them. So we have our reaction. I'm going to balance it, of course. And this is asking us what volume of chlorine gas. So I want volume of a gas. I am not at standard temperature and pressure. So I am going to be using PV equals nRT. Kind of knew that ahead of time. And then it gives me moles here, but that's moles of silver. So I have moles of silver, and I'm trying to find liters of chlorine gas. And it looks like I have some temperatures, although that's going to be 290. 290 when it's in Kelvin. And I have a pressure over here. So it looks like I have everything I need to solve for volume, but we need to be careful because that's moles of silver. It's not moles of my chlorine gas. So all I need to do with this one, and I'm going to pull up my map just to kind of show you, is a little itty bitty bit of stoichiometry. Because it gave me moles of one substance, and I want to get to the volume of my other substance, and I'm not at STP, I'm just going to do a quick little mole ratio in order to change moles of silver into moles of chlorine. And then, once I have that, I'm going to plug in those moles into PV equals nRT and solve for my volume. So, it really shouldn't take that long if we get to it. So, balanced again. Let's see here. I had 0.50 moles of silver, and 2 moles of silver react with 1 mole of chlorine. Stopping and calculating gives me 0.25 moles of chlorine, and that's our moles that I'm going to use as my N in PV equals nRT. But since I'm solving for volume, I'm going to go ahead and rearrange that. There's my N. My R, let's look, my pressure's in ATM. So the R that I'm using is 0.0821 T. It disappeared, but that was 290 once I changed that to Kelvin, and 0.950. Solving for V, plugging all of this in and keeping 2 sig figs is going to be 6.3 liters. It's not too bad. Some normal stoich up here. And then once we get that answer, we just plug it in and solve the same kinds of equations we've been solving for the last couple of weeks. Okay, let's do another one. This one, this balanced equation is crazy. It's one of those odd even rules, so our numbers get kind of big. This question is asking us for liters. I'm once again not at STP, so I'm not standard. And I'm starting with grams. Okay, so looking back at my map over here, I'm starting with grams. Oop, that's not my map. Here we go. I'm starting with grams, and I want to end up at my volume. So this is actually going to be very similar to what we did before. Before I was just starting here. The only extra step is going to be using that molar mass to turn grams into moles, and then I'm still going to turn moles into the moles of what I'm looking for before I use PV equals nRT. So let's go do it. I've got 65 grams of octane. And if I add up that mass from the periodic table, that's 114.232. 1 mole on top. And then for moles of this, I'm trying to find liters of carbon dioxide. So that's a 2 to 16 ratio. Okay, and that's where I have to stop, actually. I wanted to keep going. My instinct is to go back to grams, but I want to stop at moles so that when I get this answer, I can plug it into PV equals nRT. So solving this actually gets me 4.55 moles of carbon dioxide, and that's going to be my N. We're still solving for volume, so that's going to be nRT, P. Here's my N I just found. My R is going to be 62.4 this time because my pressure is in mmHg. That temperature is 300. Just an even 300. I swear that's a 3. There we go. And then my pressure, 560. Multiplying and dividing, that gets me 152 liters as my final answer of CO2. Whew. So, a little bit longer, but not too bad. One last problem. I want you to work this one out. This one is actually going to be worked out just like the next problem that I'm going to work out with you. There's just one last twist in the last problem that I kind of wanted to deal with first. So, you do this one. You can do it. But maybe watch me do this next one first, because this next one is going to be worked out the same way. By the way, you're welcome. It's balanced. So, balance this reaction. This one is trying to find grams. So I'm trying to end up with grams. And I'm starting with liters of hydrogen gas. And I am not at STP. So I'm going to have to use PV equals nRT. In addition to that, notice that it says the total pressure, and it gives me the partial pressure of water vapor, so I don't have to go and flip back to page 7. So before I do anything else, I'm just going to make a little note that my pressure is going to be equal to this minus that, which just so happens to equal 640. So this is the actual P that I'm going to be using in there. But let's take a moment to look at our map because I'm trying to find grams from liters. So I'm starting at volume, not at STP. I'm trying to get to grams. So my first step is going to be to take these liters to moles using PV equals nRT. I'm going to be solving for moles, solving for N. Once I get that number, I'm going to start my dimensional analysis. And I'm going to turn those moles into the moles of what I'm looking for, and then those moles into grams. So, same way when you solve your question number 3 on your own. So, starting with PV equals nRT. I'm trying to solve for moles, solving for N. And N is going to be equal to PV over RT. Pressure is... Oh, I erased all of that hard work that I had done. Let me pull that back up. And here we go. So, now solving for N. My pressure is 640. My volume was 6.5. R, based off of those mmHg, is going to be 62.4 again. And my temperature is going to be 303. Solving for this N, I'm getting 0.220 moles of hydrogen. And remember, this is our N, but I'm going to use this as my given so that I can take these moles of hydrogen, and my goal is to get grams of sodium. So here's my hydrogen, here's my sodium. So I'm going to put that 1 mole of hydrogen on the bottom, 2 moles of sodium on top, and then I want grams, so I'm going to have to keep going using the molar mass of sodium, of course. grams sodium. Get messy as I try and do more and more things, but now we're done. And this equals 10.1 grams of sodium. Wow. So set your problem up like this when you're working that question number 3. First, start by solving for n. Get that answer and use that to start your stoichiometry. And you're going to do very similar 2 steps here to get your answer. This answer to question number 3 should be between 15 and 20, just to make sure that you've done it right. So, good luck. Make sure you do those problems. If you want to get your stamps on both of these pages, finish out strong, because we are having our test at the end of next week. So, come in if you got questions. Good luck.